have a review class on Monday. We have advisory next Wednesday. So I'm gonna delay the test until Friday. But the review class will be Monday. Originally, I thought that Friday would be a shortened day because the Ministry of Education evaluates our school about every 5 years, give or take, and they're gonna be here Thursday, Friday. In years past, the Friday involved shortened blocks where the staff would meet with these evaluators. At the end of the day, that's still happening, it's just not gonna be accompanied by short block. So as far as I know, Friday is a full day. So that will be chapter 2 test day. I will try to get these things marked in time for the marks being due from me on the following Tuesday. But I'm not gonna put any of them in Power School until all of them are marked. In other words, I don't want one class to have 2 tests on the reports and another class have only 1. So I'll do my best. For sure the lab reports will be on there, but I can't necessarily promise that the test will be. I want to pick up our discussion on a topic that we did last year in Science 10. Why is this so late?
You had to staple it.
Sorry?
You had to staple it.
And that's naming covalent compounds. What I'm going to end with are 2 things that one of them we touched on last year, one of them we didn't, and that's hydrates. So if we look at the bottom of page 93. Again, names and formulas of binary covalent compounds. And the reason I want you to put that in there again is because there are binary covalent compounds that are not molecular. So just because it's a covalent compound does not mean it's a molecule, and a great example of that is silicon dioxide. Binary compound, but it doesn't exist as molecules, but it is covalent. So the vast majority of covalent compounds are molecules, but not all of them. So you can't use the term synonymously. Gary makes a good point here, introducing how we name these things. Any cation and anion combine in a single ratio that's easily predictable from their charges. Indeed, that's the only thing the formula represents. It's the smallest integral ratio that's neutral. On the other hand, 2 nonmetal atoms may share electrons and combine in several ratios. Therefore, the name of the molecular compound must reveal its formula to distinguish it from other compounds of the same 2 elements. And organic chemistry is full of examples like that. And then we don't even get into how those atoms are connected to each other. The point Gary's making here is you need to use prefixes for binary covalent compounds because the formula does not represent a ratio. It represents the actual number of atoms that are there. And we've used, I think I've used this example in class before. That's a molecule. So is that. So is that. they all have the same ratio, 1 to 2. They're different compounds. They're binary covalent compounds, where even though the ratios are the same, they're different compounds. Now, I don't know that that's a great example, because organic chemistry has specific names for those things that don't involve prefixes. And we'll get into organic chemistry later. I'm only doing it to demonstrate the point, okay? And then a whole other layer of complexity for those is how the atoms are stuck together. In this one in particular, there's 38 ways that those can be stuck together. They're all different molecules, okay? Last year in grade 10, when we employed the use of prefixes, you got the prefixes on a data table. At least I believe you did. You don't this year. So if you see a compound composed of 2 nonmetals, you need to remember to use these things. Notice that the prefix for 7 is not septa. That's French. These are Greek prefixes, hepta. All right? Some of these you already know. But these have to be employed when you're naming binary covalent compounds. If there is only one of the first element, you don't use mono for that element. But you always use prefixes for the second element in the compound, even if there's one of them. So for example, you don't call CO monocarbon monoxide. You just call it carbon monoxide. The mono prefix is required for the second one, but if there's only one of the first, you don't use it, okay? If you remember what these prefixes are, naming covalent compounds is no more difficult than naming ionic compounds. All you have to do is name the number of atoms that are there. It also makes it much easier to write the formulas. Not always the case with ionic compounds. But with covalent compounds, as soon as you see the name, you know what the formula is. And Gary says, what's the formula for xenon tetrafluoride? There's no prefix in front of the first one, so that means there's only one of them. Tetra means 4, xenon tetrafluoride. And you look at that and you go, wait a minute, it's a noble gas. How is it forming compounds? Well, this was one of the first noble gas compounds formed, and it was actually prepared by a chemist at UBC, a guy named Neil Bartlett, in the 60s. And he took the biggest non-radioactive noble gas, which is xenon. He took the biggest because the outer electron cloud is held the least tightly. And he then reacted it with the most reactive element in the table, which was fluorine. And he formed several compounds of xenon and fluorine. Okay? Since then, with great difficulty, we've forced compounds of krypton and argon to form. Never neon, never helium, and we'll explain why later on in the year. Later on in the year, we'll actually look at that and say, okay, what's the structure? How are those atoms stuck together? In addition to, here's the name, what's the formula? Here's the formula, what's the name? Notice there is more than one of the first one here. So now we need that prefix for the first element. This would be tetraphosphorus. Notice we don't change the ending of the first element. But just like ionic compounds that are binary, we change the ending of the second one to IDE. And the prefix for 10 is deca. Notice you don't reduce that to the smallest ratio, because that's not what the formula represents. It represents the actual number of atoms in the molecule. And again, by way of, for the most part, review of grade 10, nitrogen monoxide, NO, just like carbon monoxide. Quinn, am I seeing a Thomas More logo on that coat? I don't see one. Point being what? Yeah, you should probably take it off. Sorry? You don't know what the dress code?
No, I don't have a uniform shirt.
Well, Go down and check with the folks downstairs, they may have one for you. NO, nitrogen dioxide, NO2. Notice there's no prefix in front of the nitrogen, which means there's only one of them. Here there are prefixes, dinitrogen tetroxide, and normally we don't write tetraoxide. We just go tetroxide. So that would be N2O4. Dinitrogen trioxide, N2O3. Very straightforward. And then the flip side, here's the formula, what's the name? Phosphorus pentachloride. Sulfur dioxide. Not monosulfur, just sulfur. Carbon monoxide. Diphosphorus pentoxide. If you learn the prefixes, it doesn't get any more complicated than that, okay? Now, you know you need prefixes when the two elements in the binary compound are both nonmetals. That guarantees the bonding's covalent. But even if it's not a molecular compound, you still have to name it that way, okay? Now, up till here, that's really grade 9 and 10. This is something you haven't seen before. Let's say we took copper 2 sulfate and we evaporated it to dryness from an aqueous solution. What you'd end up getting would be a blue crystal that doesn't only have copper 2 or sulfate ions in it. As the water evaporates, the molecules become locked in a crystal in a specific ratio with the ionic compound. In other words, the spaces between the ions allow for water molecules to attach themselves to that crystal lattice in a specific number. And very often, that combination of ions, positive ions, negative ions, and molecules, particularly for transition metals, ends up having a color. We can't just name it copper 2 sulfate because there's water in it. And those are called hydrates. And the name for hydrates has 3 words, not 2. Copper 2 sulfate without water in it is called anhydrous copper 2 sulfate. And that's just the name, copper 2 sulfate. It's a white salt. But when we evaporate it to dryness from a solution of water, there are 5 water molecules that get locked in that crystal. And we have to name them. So there's an ionic component to it, where we just name the ions, but there's also a covalent component to it, which requires prefixes. And the name of that compound can easily be seen from the formula. So that's copper 2 sulfate, or anhydrous, without water. But the hydrate, we put a dot there, and then we write the number of water molecules. And now we just name it left to right. Copper 2 sulfate, pentahydrate. And the color of copper 2 sulfate pentahydrate is kind of the color of this rag, okay? One of the labs we're gonna do, you guys are gonna take copper 2 sulfate pentahydrate, which is a nice blue color. Nice blue, but also very poisonous. And you're gonna put that dry hydrate in a test tube and heat it over a Bunsen flame. And as you heat it over the Bunsen flame, you're gonna remove what we call the water of hydration. And you'll see that blue crystal turn into a white anhydrous, okay? So copper 2 sulfate pentahydrate, let's see, looks like this. You can pass it around, just don't taste it.
Poisonous?
It's only blue
You gotta do the
because of the water of hydration. It doesn't smell. Okay, you don't have to waft it. Don't put your face in it. Just look at it. Okay? And the number of water molecules and the spaces between the ions and how the ions pack will dictate the color that we see. So as Gary tells us here, these salts are called hydrates. Many salts are supplied as hydrates. So copper 2 sulfate pentahydrate is basically how copper 2 sulfate is purchased. If you want to remove the water of hydration, you would heat it over a Bunsen flame. We can order anhydrous. It's a little more expensive because that process will have to be done. Okay? If you take white copper 2 sulfate and dissolve it in water, instantly it turns blue because those copper 2 ions, the little 2+ ions, attract water molecules around them. And you'll see that in, again, that same lab I'm referring to. The water in a crystal doesn't usually present a problem, as most salts are destined for aqueous solutions anyway. In other words, if we dissolve this in water, we're putting it in water. So the water molecules that are locked in the crystal are freed, but it doesn't matter because we're in a water environment. The same prefix used for naming molecules to precede the term hydrate. I'll show these folks too. You guys seen this yet? Okay. Now that's just one example. I've got several others. And depending on the charge on the cation, and the charge on the anion, and the ratio in the crystal, and the spaces available to water, when that solution is evaporated to dryness, we get different numbers and we get different colors. Generally, warming a hydrated salt will usually remove the water from the crystal. The term anhydrous refers to the form of the salt without water. Some anhydrous salts are hygroscopic, which means they can absorb water from the air to form hydrates. So if you take, for example, magnesium sulfate, anhydrous magnesium sulfate, and you open the top of that jar, it will absorb water vapor from the environment. And it'll eventually form magnesium sulfate heptahydrate, 7 water molecules. It won't be colored, but it will be the hydrated form, okay? Let me show you a couple others. So copper 2 sulfate evaporated from water gives us pentahydrate. Copper 2 chloride evaporated from water gives us a dihydrate. And the dihydrate is a bit of a different color. It's kind of a greenish turquoise. That's copper 2 chloride dihydrate. Okay? This is copper 2 sulfate pentahydrate. And the different colors have to do, for the most part, with the different number of water molecules. Because if you drive off the water of hydration in both, you're going to get white crystals. Okay? Here's iron 3 chloride hexahydrate. And this one is kind of brownish, kind of a rust color. Okay? Now, I don't know if I'm going to pass all these around, but I'll just probably leave them there for your viewing pleasure at some point. This is cobalt, also a hexahydrate, but it's a nice dark red. Okay?
Nice color.
That's cobalt. It's the old OUS, but it's basically cobalt 2 chloride. And then to name it, we would write hexahydrate because there's 6 water molecules. Sometimes the name on the jar just has 6 hydrate or 4 hydrate, but the correct terminology is the prefixes. Okay? Chromate and dichromate are different colors when evaporated from water. Dichromate is a bright orange. And if you look at the name here, this one is a dihydrate. Okay? And then chromate is yellow.
It's like pastel yellow.
Spatula. So the different colors that we see are a result of the different number of water molecules locked in crystals, okay? You don't have to remember the colors. All you have to do is, given the formula, write the name, given the name, write the formula, okay? And Gary gives us sample problem with here's the formula, write the name, and here's the name, write the formula. Now this is not a very common hydrate of copper 2 sulfate. What is the formula for copper 2 sulfate? Heptahydrate. Notice 7 is not septa, it's hepta. So, and notice the dot goes right between the top and the bottom. So it's not down here, it's right in the middle. And that shows you that for every one of these formula units, there are 5 of these locked into that ratio, okay? What is the name of this compound? Well, that's a sodium ion, so the first word is sodium. That's the acetate ion. So the second word is acetate. And the third word has to be how many waters there are. So sodium acetate trihydrate. This one isn't colored. Usually the hydrates of the transition metals are the colored ones, okay? Write the formula for each of the following hydrates. Why don't you give 1 and 2 a try? And then I'll give you the answers. Although you could have checked them. I believe I asked you to do this for today's class. And remember, the prefixes are something you guys have to learn, okay? You don't get a table of prefixes. Notice each of these things have a 3-word name. Each of these things would have to have a 3-word name. Positive ion, negative ion, how many water molecules? Anytime you're going to be writing a test from now on, you're going to get a periodic table and you're going to get a table of ions. Periodic table will be the one on the back cover, and the table of ions will be the one on the back of the second last page. Barium chloride dihydrate. Barium chloride dihydrate. Sodium carbonate monohydrate. Sodium is 1 plus, carbonate's 2 minus. You don't have to put a 1 in front of the water, you just put 1. Iron 3 nitrate monohydrate. Iron 3 nitrate. There's that. Monohydrate. Mono means 9. Barium hydroxide octahydrate. This isn't colored, that isn't colored, that isn't colored, but that is. Cobalt 2 chloride hexahydrate. That's this dark red powder, okay? Iron 3 chloride tetrahydrate. Notice there's no space between the tetra and the hydrate. One word, okay? 3 separate words, but the hydrate's one word. Sodium dichromate dihydrate. That's the orange one. Magnesium sulfate heptahydrate. That's what anhydrous magnesium sulfate will turn into if you basically leave it out in the air for a while, okay? It'll absorb water now. And that's not colored, that's colored, but not because of that. Okay? Yeah, so there's no real mystery to it, you just have to know the rules. So these are different than what we talked about last year. Everything we named last year had 2 words in the name. Positive ion, negative ion, non-metal, non-metal. Here we have a mixture of both covalent and ionic. So that's the point behind the 3 words. You need the prefix for the covalent part, right? And there's a number of examples in review, none of which are any more difficult than what we just did. And the last naming item is something we did touch on last year, although, if I remember correctly, the Science 10 book did not really do an adequate job. I actually like the way Gary describes acids. An acid can be thought of as one or more hydrogen ions bonded to an anion. But in actual fact, acids are covalent compounds, and Gary uses the term induced. So acids are actually covalent compounds that can be induced to form ions. Induced means there's no ions there initially, but they can be convinced to form ions, and usually that means put them in water. And acids that form ions 100%, we call those strong acids. Acids that only produce some ions in water are called weak acids, and that's a topic in Chem 12. So Gary tells us here, acids are a special type of molecular compound that can be induced to form ions. There are different categories of acids depending on whether they have only 2 elements in them. We call them binary acids, hydrogen and one other thing. Or if they're not binary acids, then we look at the negative ion that is there. And that means you've got a polyatomic ion. And depending on the polyatomic ion that's there, we have rules for how we name the acids. The rules for naming acids depend on whether the anion contains oxygen. If the anion doesn't contain oxygen, the prefix hydro precedes the name. Right, the prefix hydro usually precedes the name. Okay? What Gary's point is, if it doesn't have oxygen, then it has to be a binary acid. That's not true. Okay? What is true is if the naming of the anion, if the anion ends in "ide", then the prefix hydro is there. Okay? So probably the best way to describe this is categorize ions as binary acids and oxyacids. Binary acids are 2 different elements. One of them has to be hydrogen. So binary acids are named hydro something ic. true the vast majority of the time. If it starts with hydro and ends with ic, it's a binary acid. There are a couple of exceptions though, okay? This is also true for acids whose negative ion is an ide ion. And that's what this line is about, okay? Based on the name of the anion form. If the anion that forms ends in ide, vast majority of the time that's a binary acid. But there are several exceptions. Can you find an anion on your table that ends in ide that is polyatomic? There are two of them. Yeah. Cyanide, and what's the other one? Hydroxide. We don't worry about the hydroxide anion when we connect it to hydrogen, because hydroxide anion connected to hydrogen makes water. But if hydrogen is connected to the cyanide ion, that's not a binary acid. But because that ion ends in ide, we follow this protocol, okay? So you may want to add here, that's kind of the exception, but binary acids or acids containing ide anions are named this. Now 99% of the time they're the same thing. It's got an ide anion, the ion is a monatomic ion. But this is an acid, but we still employ this protocol, okay? So let's look at some simple examples and then we'll build this. So when you throw those molecules in water, they come apart into ions. That's the chloride anion, so this is hydrochloric acid, okay? That's the bromide anion, so it's hydrobromic acid. That's the iodide anion. You may want to write this down unless you have a photographic memory. The last test proved to me most of you do not. Hydrochloric. That is based on this, okay? Hydrobromic. Hydroiodic. Now, you might think, okay, that's the sulfide anion, so we probably call it hydrosulfic, but for sulfur, we add an extra syllable. So this is actually, it's still hydroic, but it's not hydrosulfic, it's hydrosulfuric. So the hydro and the ic are still there, it's just that we add that extra syllable. Why they do that, I actually don't know. Okay. This one is hydrofluoric. And notice fluorine is not F-L-O-U, it's F-L-U-O. So it's correctly pronounced fluorine, not fluorine, but it's hydrofluoric acid. F-L-U-O-R-I-C. Now all of those are binary acids, so that applies. But that one is not a binary acid, but yet Cn minus ends in ion. And if it does, we gotta use the hydroic protocol. So if that's the cyanide anion, the name would be hydrocyanic acid, okay? And that's the only exception as far as I know based on that table, okay? So the hydro is still there, but because that's an because it's an anion, but hydrocyanic. Right? And again, that's the only exception. It's kind of a contradiction that the acids that have the smallest formulas have the longest name, the hydroic. Oxyacids don't, okay? You're never gonna see an acid with oxygen in it that begins with hydro, okay? Binary acids don't have oxygen in it. Oxyacids have what looks like a polyatomic anion in them, even though it's actually a molecule, okay? And we're gonna categorize those acids based on the negative ion that's there, as David tells us. So we call those oxyacids. They're not binary, because they got hydrogen and oxygen and a third element, okay? But again, the name is based on the negative anion. An oxyacid has a negative ion in it, at least when you put it in water, that is either 8 or ite, okay? Oxyacids containing eight anions. And you know what? It might be better. There's an exception here too, but I'll get to that in a second. Oxyacids containing 8 anions are named something ic acids. There's no hydro prefix, okay? So these, as soon as you look at the negative ion that will form in water, all you do is name it with an ic prefix. So this compound is actually covalent. But we put it in water, and hydrogen ions separate from that ion. What do we call that ion? What's SO4 with the 2 minus charge? Sulfate, which means the name of the acid. Remember, for sulfur we add that extra silver, so this is sulfuric acid, not hydrosulfuric, just sulfuric. Why is that? Because that's the 8 anion. Sulfuric acid. So you have to recognize the anion that's in there, even though it's not an ion until you throw it in water, all right? What are some other 8 ions in your table? Give me another one. Phosphate. I'm glad you picked phosphate. Phosphate has a 3 minus charge. Just like sulfur, for phosphorus, we add an extra syllable. Even though the ion is called phosphate, we don't call it phosphic acid, we call it phosphoric acid. So that extra syllable for sulfur and this extra syllable for phosphorus is still in play, right? We don't do it for any other elements. What's another 8 anion? Sorry? Nitrate. What do you think the name of this acid is going to be? If 8 ions make ic acids. Take a guess. 8 ions make ic acids. What would this acid be called? Nitrate. Yeah, nitric. Nitric's a very reactive acid, okay? Nitric acid. Give me some more, besides nitrate.
Chromate.
Chromate. Now this one is not, doesn't fit into the category, it's actually a covalent compound. Chromium is a metal, so chromate is a bona fide ion, okay? It's not a molecule that turns into ion. But if that's the name of the anion, chromate, then the acid should be called, you guys, 8 ions make ic acids. Chromic, yeah, that's simple. Chromic acid. What's another one? Chlorate. Chlorates as an ion, it's 1 minus, so that's that. And if it's the chlorate anion, what would the name of the acid be? Chloric, yeah. Can you find any others that end in 8? Not with the prefix, not the per or hypo. Yeah. Carbonate. What do you think you call that acid? Carbonic. Carbonic acid is what we get when we add carbon dioxide to water. And the word acid is actually Latin. Acidus means sour. So when we add carbon dioxide, for example, to water in a soda stream, we put the carbon dioxide in, then we put the top on. And if we drink it with the carbon dioxide, what the carbon dioxide does, it comes out of solution as carbon dioxide gas. And that's the fizz we taste. It also tastes a little sour. But if we open the soda stream bottle after we put the carbon dioxide in and wait, all the carbon dioxide is going to leave water because it's not that soluble anymore. But as long as it's under pressure, as long as it's sealed, the carbon dioxide will stay in solution. So soda pop, the fizz you get is carbon dioxide, okay? So that's carbonic acid. It's an unstable acid, but the carbon dioxide will remain in solution as long as it's under pressure. Look at the very bottom on the right-hand corner. What's the name of that ion?
Thiocyanate.
Thiocyanate. It ends in 8, but there's no oxygen. So here's the exception to this one, just like hydrocyanic was the exception to the hydroic. Because it ends in 8, that's the thiocyanate anion. That acid is named the same way. If it's thiocyanate, what do you think we call the acid? If 8 ions make ic acids?
Thiocyanate.
Thiocyanic. Yeah, the 8 becomes ic. So that's thiocyanic acid. And that's the only exception to this rule that you'll need to worry about associated with your table, okay? Now notice there are also ite anions in the table. So many of these have ite counterparts, like that one and that one. I don't know if that one's on your table, but there is an ite counterpart to that. So we gotta change this a little bit. oxy acids containing anions are named not something it, but something us, O-U-S. And let me write some examples on the board. So, because it's the sulfite anion, it's not sulfuric acid, it's sulfurous acid, O-U-S. I don't think PO3 3 minus is on your table, it's not a common ion, but it's called phosphite. So this would be phosphorus acid. Nitrate makes nitric acid, but nitrite makes nitrous acid, because that's an IN. There is no chromite, but there is a chlorite. So whereas chlorate makes chloric acid, chlorite makes chlorous acid. And there's no carbonite either. Okay? And as you learn in Chem 12, the more oxygens in an oxyacid, the more likely it's going to be a strong acid. Remember the series for chlorine and oxygen. Remember we had chlorite, chlorate, perchlorate, and hypochlorite. There are acids like that too. So if instead of chlorite, what if we had hypochlorite and hydrogen? The ite's still there, so the OUS is still in a name. We just add the prefix. So because that's hypochlorite, the acid would be hypochlorous. So it still ends in us because that's an anion, but it's also got the hypo prefix, so we just continue that in the name of the acid. Hypochlorous because this is hypochlorite as an anode. That's the hypochlorite anion. So we stick an H plus on it, it's hypochlorous acid. And the other member of that series, ClO4, 1 minus, is perchlorate. So if the ion ends in ate, the acid still ends in ic, but we add the prefix. So because that's the perchlorate anion, that's perchloric acid. So that stays there in the name. The ic is there because the ion ends in ate. The us is there because the ion ends in ite. Okay? Can you see another per ion in there that ends in 8? One more, I believe. Permanganate, that. So that acid would be what? This is the permanganate anion. So if the perchlorate anion makes perchloric acid, the permanganate ion would make permanganic acid, right? Again, the per is still there, but because it ends in 8, it has to, the acid has to end in ic, okay? Now, I think we probably covered more than Gary has given us here. What acid has the formula HNO2? Nitrous acid, because that's the nitrite anion. So it's an oxyacid whose anion is ike, it's OUS. Write the formulas for each of the following acids and write the names of the following acids. I don't like the way he's done 2A. Hydrofluoric, hydroic means it's a binary acid, no oxygen in it. So that'd just be HF. Hypochlorous, we just did it. HClO. Phosphoric, ic means it's an 8 anion, so that's H3PO4. Hydrosulfuric, hydroic means it's a binary acid, so that's H2S. I don't think you're ever going to see that acid written that way ever again, but I think he did it to show you that there's the negative ion. What do we call that negative ion? In your table. What's CH3COO minus called? There's two names, but use the first name. Acetate, right? Is it not acetate? Acetate's an 8 anion. So what do you think the name of the acid is? If 8 ions make it acids. Acetic. Yeah. 5% acetic acid is vinegar. And you don't have to be reminded that vinegar tastes sour. Okay? There are thousands of acids. Okay? Most of them are carbon-based acids. Acetic acid is an example of that. Okay? And again, we'll get into how to name organic acids later. I don't know that I want to go into too much of naming organic acids now, but for now we'll just go, ic acids come from 8 ions. Okay, so that's acetic acid. You're never going to see it written that way. The vast majority of the time you're going to see it written that way. Okay? And that's really the two ways to recognize a formula for an acid. Starts with hydrogen, except for water, or it ends with COOH. Okay? Now you might wonder why they just don't write CO2H or H2C2H3O2. Well, because this tells you something about the structure. We'll do that later in the year, but the carbon connected to the hydrogens is different than the carbon connected to the oxygens. And we don't write CO2 because in a compound, oxygen doesn't usually like to stick to itself. So one of those oxygens is doubly bonded to the carbon, the other one is singly bonded to the carbon. But that carbon and that carbon are completely different. And when you put that in water, that hydrogen ion comes off, forming the acetate anion and hydrogen. And the other name for it in your table is ethanoate, and that's organic chemistry. And we'll get into that, time permitting, in May, give or take. Carbonic acid, because that anion is carbonate. That anion is sulfite, so that's sulfurous acid. That's a binary acid, so it's hydroic, and because that's iodide, it's hydroiodic. And that, ladies and gentlemen, pretty much finishes the chapter. Gary gives you what I consider to be a reasonable practice, formula writing and naming. But as I've said several times, given the fact that I didn't teach most of you last year, I don't know how many of you, if any, struggle with formula writing and naming. You have to be able to write formulas correctly. You have to be able to name compounds correctly. When we get into quantitative chemistry, and you have to calculate things like molar masses, given only a name, if you don't have the formula, you obviously can't determine the mass. if you're balancing equations when all you're given is the names of the reactants. Obviously, if the formulas are wrong, the equation will not be balanced properly. So you guys have to solve the formula writing and naming issues. You've been seeing it now for, well, I guess 3 years. Practice formula, check your answers. If you keep getting it wrong, you're gonna have to go back and review the material in the book, okay? I didn't assume you're all experts, I taught the material, but except for the hydrates and maybe the level of detail we went into in the acids, the rest of it is really what you guys did last year, okay? And that's why Gary doesn't put more pages in it, because the assumption we all make is that you learned it last year, really all you have to do, with some minor exceptions, is remember it, all right? So, the plan is for Monday, we have a review class. Remember, it's not just this section, it's the chapter. So, the last review class we had, the first review class we had, there were maybe 3 or 4 people that asked questions. Everybody has questions. And that was proven to me when I marked your tests. But I can't get inside your head and find out what you're not sure of. You've got to tell me. And remember, if you've got a question, there's probably half a dozen other people wondering the same thing. And the best question's a specific question. I'm not sure about separation techniques, or I'm not sure what this separation technique involves. Or I'm not really sure on the drawings we went into in terms of the heating curve, what it meant. I'm not that fluent on the difference between, say, evaporation and dryness and distillation. Like, what's the difference? Those types of questions I can handle. But I probably can't help you too much with, I don't know how to write formulas. That's on you. You gotta tell me which formulas you're having trouble with, or what part of formula writing you're struggling with, but we can't go through the material from scratch. Give me specific examples of where you wrote a formula and the answer was wrong, or on page this, I read this, but I'm not sure what it means, or I was away that day, could you maybe review this? Okay? And if you can, think back to also what I said, what makes a good test question? All right? And one of them was the heating curve. You know, we didn't only just call it heating, we also referred to cooling. And we overlaid on that an impure substance. So whenever I do that, whenever I add extra stuff or spend time on it, it usually means I consider it to be important, and that means, as likely as not, it could be a test question. Okay? So, I will leave the rest of the period to you guys to construct review questions. If the review's Monday, what are we gonna do Wednesday? As far as I know, Monday's a full block. That's why I wanna give it a review class. If we don't fill Monday's period up with review, I'll start chapter 3. I'm gonna start chapter 3 anyway on Wednesday. It's just that none of it will be on the test. And in as much as some of the stuff we've done has been reviewed, none of what we do in chapter 3 will be reviewed. It's all brand new stuff. That's really technically where grade 11 chemistry starts. We start talking about the mole. And we can't speed through that because it's too foundational, but it will be brand new stuff. But don't worry about that for Monday. Just let's see if we can fill that entire period up with you asking questions and you answering.